Imagine dropping a delicate, glass-enclosed water flow meter directly into the center of a raging river. The sheer force of the current would shatter the mechanism instantly. In electrical engineering, that fragile device is the galvanometer. Its internal coil and needle are highly sensitive, perfect for detecting tiny trickles of electricity. To measure massive currents in actual circuits, we build bypass channels to safely divert the flow around it. When we package a galvanometer with one of these bypasses, we create an ammeter. An ammeter measures electric current and must always be placed in series, directly in the path of the circuit we want to measure. This handwritten note lays out the requirements. Because it sits directly in the line of flow, an ideal ammeter must have exactly zero resistance. Otherwise, plugging it in would accidentally slow down the very current it's trying to measure. To see how this is achieved, look at the diagram inside this dashed yellow box. We convert a galvanometer into an ammeter by connecting a small resistance, called a shunt, in parallel. As the main current, I, enters the device, it reaches a junction and splits. A tiny fraction, I sub g, trickles through the galvanometer. The remainder, I minus I sub g, is forced down through the shunt resistor, R. Because the galvanometer and shunt are connected in parallel, their voltage drops are equal. We multiply the top branch's current and resistance, setting it equal to the bottom branch. Rearranging gives us the boxed equation to solve for the exact shunt resistance. Notice the mechanical contradiction. To function, an ammeter must connect to the outside world in series, but to survive that connection, its internal wiring relies on a parallel structure. Let's apply this internal structure to a calculation. Look at this word problem, which states that 0.2% of the main current passes through the galvanometer. The diagram on the right translates this. If a hypothetical 100 amps enter the system, only 0.2 amps go through the meter, pushing the remaining 99.8 amps down through the shunt. By setting the voltage drops equal again, we substitute the values. 0.2 times the galvanometer's resistance, G, equals 99.8 times R. Dividing both sides by 99.8 simplifies the math, proving the necessary shunt resistance is G over 499. Stop here. Finding R is a common trap. R is only the resistance of the shunt branch. To find total resistance of the ammeter, calculate the equivalent resistance of the parallel circuit using the product over sum formula, R times G divided by R plus G. Substituting our value for R into that formula yields a final answer of G over 500. By bridging a high-resistance component with a tiny fractional resistor, the overall resistance of the device plunges, approaching our target of 0. Now let's tackle a more complex variation. These side-by-side diagrams illustrate a scenario where a galvanometer is shunted, but the physical requirement is that the main current flowing through the circuit remains completely unchanged. If the current cannot change, Ohm's law dictates the total equivalent resistance must remain identical. The first equation sets the original isolated resistance, G, equal to the newly shunted parallel resistance, plus a new external series resistor R that we insert to compensate. Walking through the algebraic rearrangement, we subtract the parallel term to isolate R. Finding a common denominator allows us to combine terms, canceling out the GS variables and leaving us with R equals G squared over G plus S. The math proves a strict physical rule. Whenever you add a parallel shunt, overall resistance drops. To keep the electrical flow balanced, you must precisely pay back that lost resistance by placing a new component in series. Measuring potential difference between 2 points requires the inverse logic. Looking at these rules for the voltmeter, we see it must be connected in parallel, and to avoid pulling any electricity away from the circuit it is measuring, an ideal voltmeter requires infinite resistance. The diagram on the right shows how this works internally. To safely sample voltage without stealing current, we choke the flow entirely by adding a massive resistor, R, in series with the galvanometer. Because this is a series setup, total voltage equals the tiny trickle of current, I sub G, multiplied by the combined resistance of G plus R. Rearranging the variables gives us the boxed equation to calculate exactly how massive that series resistor must be. The physics demands completely different survival strategies. While an ammeter needs a massive bypass to avoid burning up, a voltmeter acts as a near-infinite roadblock. It ensures the main current completely ignores it, allowing devices like this to safely read hundreds of volts. Let's consolidate this into a side-by-side cheat sheet. An ammeter connects externally in series, utilizes an internal parallel shunt, and targets an ideal resistance of 0. A voltmeter connects externally in parallel, utilizes an internal series resistor, and targets an ideal resistance of infinity. The ultimate rule to remember for exams is this exact inversion. The way a device is connected externally is always the exact opposite of how its internal components are wired. By isolating this electrical contradiction, engineers in early environments like this historical laboratory space realized they didn't need to invent entirely new mechanisms. They just needed to arrange resistors precisely, transforming one fragile needle into the two foundational tools of electrical engineering.